Let's start off with the fundamentals, gentlemen. What is ultimately real in both your frameworks? Donald, for you, consciousness is fundamental. So what has ontological status? And Karl, are generative models and physical states realist commitments, or are they as-if descriptions? In other words, do your views compete, or could active inference nest within a consciousness-first reality? And what is space-time then for both of you? Lot to cover.
Let's actually keep us out of mystery for a couple of hours, wouldn't it?
Yeah.
I was hoping for something more ambitious. So yes, you're right that I take consciousness as fundamental, not space and time. And I would say there's two general classes of reasons for why I've chosen to go that direction. One is that high-energy theoretical physicists themselves say that space-time is doomed, that it's not fundamental. And the argument that they give is that it has no operational meaning at the Planck scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds. And so if in physics you have some concept that has no operational meaning at some point, then usually that's not a fundamental concept, and you need to find something more deep. And so as a result, the European Research Council has a multi-million euro initiative on what they call positive geometries. And there are 100 physicists, mathematicians, high-energy theoretical physicists and mathematicians who are now letting go of space-time entirely, and quantum theory. So they will not start with unitarity and locality. They're starting with what they call positive geometries, specifically things like amplituhedron, associahedron, cosmological polytopes, and so forth, that are objects outside of space-time entirely. So there's literally no notion of locality in these objects or unitarity. And yet the facet structure and volumes of these objects they're discovering encode the amplitudes for scattering processes of particles inside space-time. So that's one direction. We can go into that further, but that's one direction. So I'm listening to the high-energy theoretical physicists. Now, for most physicists, of course, they're happy inside space and time. It's the high-energy theoretical physicists who are looking at, this is their turf, and they're saying, we're the ones who probe space at the finest scales and the highest energies, and what we find is it falls apart, and we need a deeper framework. And so Nima Arkani Hamed, and others, David Gross, have said space-time is doomed and we need to find something deeper. And the ERC is putting a lot of money into it. And that's stunning. I'll just say this. What's remarkable is not only that they can compute these scattering amplitudes, ignoring unitarity and locality, they don't need them at all, but they can compute them in many cases far more easily, something that requires hundreds of pages of terms using Feynman diagrams and looking at all the different kinds of interactions that you could have, you can do in 1 or 2 terms. So you reduce, 500 pages to 1 or 2 terms, and you get the right answer. So it's sort of like we're on to something there. So that's one. So I'm taking a clue from the physicists themselves, the high-energy theoretical physicists, that space-time has been a great framework, but it's over, and it's time to think out of that box. And the second motivation has been, I've been great friends with people who are studying consciousness from a wide variety of, some cognitive science, neuroscience, and so forth for many, many years. I'm good friends with all the big players in the field, and they're brilliant. So they're brilliant colleagues and friends. And they're trying, in most cases, I would say 99% of the cases, to start with a physicalist theory. So some account of neural activity, or some kind of informational property like integrated information theory, and trying to boot up conscious experiences, get a scientific theory of conscious experiences. And so far, I'll put it this way, there are trillions of conscious experiences that humans can enjoy. If you count them all up, all the colors and tastes and smells and everything that we can experience, there are literally trillions of experiences for us to explain. And when I check and see how many specific conscious experiences the physicalist theories have explained, the answer is 0. There's literally not a single specific conscious experience that a physicalist theory has ever explained. And if I came to a scientific community and I said, look, I've got a new theory of particle physics. And people go, oh, wow, really? Oh, interesting. Well, Hoffman, what particle interactions can you explain? Like gluon-gluon interactions or electron-photon interactions? And I said, oh, I can't explain any specific particle interactions. They would say, don't waste our time. Come back when you've got something specific and concrete to show us. And that's my attitude right now. 2 things. First, these are my friends and colleagues, and I know they're brilliant. And they're working as hard as they can. And there are trillions of experiences for them to tackle, and they can't tackle even one of them with a physicalist framework. So I take these 2 clues together, and I say, high-energy theoretical physicists tell us it's over for space-time. And when we try to start with physicalism and boot up consciousness, the best and brightest can't do it on a single specific conscious experience. And so at some point, I don't want to be a fly on a window pane beating my head against that. And so I'm looking at the opposite, and I'm saying consciousness is fundamental. And of course, then if I start with that, then I've got the opposite problem. Hoffman, if you're saying consciousness is fundamental and space-time is somehow just a concept or a structure that's made by consciousness, then show us exactly how you get space-time for a theory of consciousness. So that's what I'm working on. That's the beef that I have to show is, if I start with a theory of consciousness, how do I get special relativity, general relativity, quantum field theory, and so forth? So that's sort of my opening sort of ontological point of view.
A lot there, Carl. Anything you want to add?
I will add I think these ideas I've been sort of partially exposed to by common friends and colleagues, people like Mike Levin and Chris Fields and the like, and I'm extremely sympathetic towards them. I should qualify what I say. I always look at things through the lens of the free energy principle, and crucially, the free energy principle is not a theory of consciousness. So I have a certain naivety when it comes to these kinds of conversations. I sometimes regard them as spectator sports with these brilliant people.
Right.
However, from a purely sort of, and I'm talking really about sort of schoolboy university maths. The last time I did quantum physics, it would have been the 1980s or 70s. So I can't speak with the nice fluency that we've just witnessed about the high energy physics, but certainly the basic notion that your explanation for our experience of the lived world should be background free, I think is certainly and by background free, I'm using it in the sense of Chris Fields that space, certainly. I'm not so sure about time. I think we're going to come on to time, but certainly space time as understood in a classical context is a construct. It is the product of the way that we make sense. So the deeper quest of the world, and possibly our sensorium. So I think the deeper question is, what are the mechanics and what are the physicalist principles that would afford a teleology where you could say that space-time is a construct. It's a parsimonious explanation for the way that we engage with the world, should it be there. And I think that parsimony is interesting because I sort of picked up on Don's notion. You could write down with some 21st century Feynman diagrams 500 pages of derivations, with a few expressions. Something quite fundamental about that. That is one aspect of the free energy principle in action. The ability to compress, the ability to find that minimum description length, literally that minimum homograph complexity, a description, a model of the way that the world works, or a model or an account of the world that is maximally expressive in the sense that it explains so much, yet is so simple There's something fundamental, there's no truth pointing, so there isn't in the free energy principle, but there certainly is the best kind of understanding, the best explanation for what's going on, and it will usually be the most compressed, statistically the most likely one. And of course that's the most likely one is the one that has the greatest marginal likelihood, which is the thing that the free energy lower bounds. So the way that I would approach this is, how does one lift a teleology and an understanding from the physics of self-organization, where the physics of self-organization does not assume space-time in the way that we normally do, but will manifest as quantum mechanics, will manifest as statistical mechanics, will manifest as classical mechanics. But what we really want is another kind of mechanics that has exactly this explanatory power, where we understand the teleology, the constructs, the illusions, if you want, although I'm sure Don's got a better word for it, that we talk about in terms of sort of classical physics and the things that we experience.
I agree. In fact, it's in some sense that free energy principle kind of idea that has pushed the physicists on this. They discovered these simpler forms of scattering processes, descriptions, because they needed to. And we were trying to build these colliders, and the physicists who are doing the experiments were saying to the theorists, you're giving us 500 pages of algebra for one interaction. We can't do this. Even our supercomputers, we're not going to be able to analyze our data. Please, can you simplify your math? And so two mathematicians, Park and Taylor, worked on this, and they got several hundred pages down to like 30 pages. And it was like a miracle. Everybody was going, holy smoke. It was like genius stuff. And then Park and Taylor were into it so much that they all of a sudden guessed a deeper solution. And they published this deeper solution, and it turned out to be right. And so people are going, holy smoke, Feynman diagrams, by the way, are correct. They give you the correct answer. So it's not that they're wrong, but it's this free energy kind of principle that they're unbelievably complicated and apparently unnecessarily complicated. So the question was, is this a one-off? So maybe we just got lucky. This particular kind of scattering, there's a simplified way, but in general you can't. But it turned out to be the tip of an iceberg. And Ed Witten and his graduate students found something called the BCFW recursion relations in the early 2000s. And that seemed to show again that there was some kind of data compression going on here. You didn't need the Feynman diagrams. And then Nimar Kani-Hamed and his discovered the amplituhedron in 2013, and now they've been finding the associahedron and so forth, the cosmological polytope. All of a sudden, the European, the ERC all of a sudden said, hey, this isn't a one-off, this isn't a two-off. There seems to be something lurking here, and they're putting, 10 million or 100 million euros into, I forgot how much, but there's lots of people working on this right now. And it's they're really uncovering stuff. Now, it's not fully general yet. They're still trying to, because you think about it, they're going outside of space-time. How do you do that? How do you think entirely outside of space-time? So you don't have the notions of locality or unitarity. You've got to just be a free thinker and postulate these structures outside of space-time with the constraint that you can then, press them back into space-time, project them back into space-time somehow, and get the scattering amplitudes, show where unitarity and locality come from. So it's you can imagine it's fun, but it's way out there. You have to go outside of space-time and then be constrained by projecting back into space-time. So it is, the free energy principle seems to have also been, minimizing the complexity of the description seems to be a guiding principle. The fact that you can do it suggests that space-time isn't fundamental. There's a much more fundamental realm. And the point is that when Feynman diagrams force you to make unitarity and locality explicit, that's what they do. They're making unitarity and locality explicit. That's what it means, and it works. You get the right answer. But apparently, that's not the nature of reality. That's just the nature of this space-time representation. The reality has a much simpler structure. And when you look at it in space-time and force unitarity and locality, then all of a sudden things You can do it, but good luck. 500 pages of algebra. So it's a big clue that space-time physics isn't fundamental. Now, again, most physicists, what they're doing is fine inside space-time. It's the high-energy theoretical physicists and looking at scattering at high energies where this is in your face, and now you see the Planck scale is in your face, and you can't ignore it, and you really do have to take the leap beyond. So, but for me, as a cognitive scientist, not a high-energy theoretical physicist, studying consciousness, the fact that my brilliant colleagues who are working extremely hard for many decades now on getting consciousness from physical systems cannot get a single specific case, like the taste of mint or the smell of garlic, is again telling me something that lines up with what the high-energy theoretical physicists are saying, which is it's over for space-time, and we have to think out of that box. And I think that, unfortunately, my brilliant colleagues will not be able to solve this problem because they're stuck inside a space-time framework. Most of physics can be done inside a space-time framework, but not high-energy theoretical physics. It cannot be. And consciousness is like that. It cannot be done inside a space-time framework. We actually have to step outside. And so then my hint is, well, maybe we have to step outside for the same reason. Maybe there's the same, whatever is the problem with doing consciousness inside space-time is also what the high-energy theoretical physicists are finding. There's something that's common to these two problems. And so that's what I'm pursuing.
Yeah, you said that it wasn't general, but it did remind me of the foundations of universal computation. If you trace things, through Kolmogorov complexities, someone off induction right through to universal computation, there's a common theme: keep everything as simple as possible, but no simpler. And that's, I think that's a beautiful way of describing the the simplicity that should attend any explanation. And if it happens to be at the scale you're observing your favorite thing to be observed, Lagrangian mechanics or classical mechanics with space and time, or even general relativity, then fine. But that's just one scale and one kind of sense making that that would be appropriate for that particular scale. What's your opinion about? I mean, in my world, even stochastic thermodynamics, but certainly statistical thermodynamics, requires some very, very special commitments. Largely, so the exchangeability of lots of particles, for example, which denies it a certain kind of generality that you find in formulations that are based purely in terms of probability theory and information theory. Would you include probability theory and information theory in a sort of classical space-time kind of physics?
No, I think probability theory is its own complete subject, its own mathematical subject, and it can be used in space-time settings, but it's not limited to space-time settings at all. And in fact, that's one of the things I've been pursuing now and trying to go beyond space-time is focusing on probability and the structure of probability quite heavily. And of course, the notion of Bayesian inference, right, is all probabilistic. And so one thing I've been thinking about for a while is that when we talk about like Bayesian inference, inference is about propositions, and propositions are entities that can have truth values. And you can talk about their conjunctions and disjunctions and negations and implications and so forth. And a few decades ago, when I was looking at perception as Bayesian inference with some mathematicians, I just asked the mathematicians, I said, we're talking about probabilistic inference, and so probability measures must have some kind of propositional structure, logical structure. So what is it? You're the mathematicians, tell me. So the mathematicians that I was working with sort of scratched their heads. So we sent off a graduate student and said, okay, well, go, surely they've done this. Find a non-trivial propositional structure on the space of probability measures. Because I didn't want to just be talking Bayesian inference without having a logical structure for probability measures, man. What are you talking about if you don't know what their logical structures are? Well, came back after several weeks, we couldn't find any non-trivial. So we then started saying, okay, well, what do we have to do here? Because this thing seems, not properly founded if we can't even talk intelligently about and, or, negation, and implication among probability measures. And so we worked on it, and we discovered a logic on probability measures. And we call it the Lebesgue logic because it's based on the Lebesgue decomposition theorem. And it actually turned out to be simple, that one probability measure entails another if it's a normalized restriction. So if I can take the probability measure, the big probability measure, restrict it to, look at just a subset of its states and take the normalized restriction of the big probability measure to that subset of states, you get a new probability measure that's smaller in some sense. And you define that smaller probability measure entails the bigger one, and that's all you need. It turns out that was the only definition we needed, that one probability measure entails another if it's a normalized restriction of the other. That was it. And then you get an entire non-Boolean logic that comes out of this thing. It's quite beautiful. So there is a logic of probability. And so when we talk about Bayesian inference, there actually is a mathematical structure that's non-trivial, that says that we're okay to talk about Bayesian inference as, some kind of propositional inference. And it turns out that Bayes' rule then appears as the and of the logic. They typically call, in this work, the implication is called a partial order. So you have a partial order, and you have meet and join. And so the meet, the and, is what the Bayes rule turns out to be. It's just the meet or the and of this big logical structure. There is a mathematically precise framework for talking about Bayesian inference, and actually knowing what we're talking about in terms of logical structure and propositional calculus and where Bayes' rule fits in. But that's just for static probability measures. Now, when we come to processes, probabilistic processes, there's a question that, we want to. I can't talk now about processes inside space and time, right? I'm trying to model consciousness as some probabilistic process outside of space and time. And so I agree with what you said earlier, Carl. We want the simplest thing that we can put down, right? We want as few assumptions and as simple a mathematical structure as possible. And for that, what we've said is, look, let's just assume the simplest possible thing here outside of space-time. And that is, there are conscious experiences, taste of mint, smell of chocolate, perception of a 3D object, whatever it might be. And there are probabilities that if I experience mint right now, that I'll experience garlic next, or whatever. So there are experiences and probabilities of transitions. So in other words, I can just write down Markov matrices. And the states are, in the case of human, there's trillions of experiences that we can have. So just there's trillions of possible states, and then there's all sorts of probability of transitioning from one to the other. And some are high probability and some are low. So the idea then is just have the notion of a conscious observer just be a conscious observer is a Markov matrix on a set of experiences. Nothing else, just that. Very, very simple. And then the question is, okay, is there some kind of logical relationship? If those are, again, these are sort of probabilistic objects, or I'd like to understand their logical relationships, how they're logically related propositions, and how the ands and ors and implications of them. And so we've discovered just in the last 18 months a logical structure on the space of all Markov chains. Because we're trying to be completely systematic here, understand this stuff thoroughly from a logical point of view. And it turns out that there's also a very, very simple partial order that no one had discovered, apparently, on the set of all Markov chains. What had been discovered is a very interesting notion of the trace of a Markov chain onto a subset of its states. So this is very different than the notion of trace that most people think about with matrices, which is just the sum of the diagonal elements. So I'm not talking about the sum of diagonal elements. That's very simple. This is something different. It's saying if I have a Markov chain on, say, 10 states, and then I say, but I'm only going to pay attention to 4 of the states. So I have a 10 by 10 matrix to start with, but I'm now going to only restrict to 4 states. So I want to get the canonical 4 by 4 matrix that is in some sense the best representation. If I can only see, if I'm looking at the world has 10 experiences, but I can only experience 4 of them, and I have this 10 by 10 which is describing that world. So here's the world, here's the 10 by 10 matrix. What is the least surprise world that I could have on a 4 by 4 matrix? And it turns out that has been known for many, many decades. It's called the trace. And there's a very, very simple formula for computing the trace of a matrix. So it's well known in Markov chain theory. So that's not new. We didn't discover that. What we discovered was that there is a logic on the space of all Markov chains. And the logic is that one Markov process, one matrix, entails another if it's a trace of the other. That's it. That's, again, a very trivial, once you know the notion of trace, you just say that's it, and that's all you need to say, and you get an entire logic on the space of all Markov chains. It's, again, non-Boolean, but what's interesting about it is two things. It's non-Boolean, but it's locally Boolean. If I take any particular Markov matrix and look at all of the traces of that matrix onto subsets of states. So look at all the matrices that are less than it in this logic. They form a nice Boolean logic. But in general, the logic is not Boolean. So in general, there's not a meet or a join between Markov chains. And with every Markov chain, if it's ergodic, if it's if it's a nice Markov chain, for a broad audience, ergodic may not mean anything. So I know it means something to you, Karl, but for a broad audience, it doesn't mean anything. So I'll just say if it's a really nice kind of Markov matrix, where you can get from one state to any other state and back in the matrix, then there's going to, in general, be what's called a stationary measure, which is the probability, how much time will I spend in state 1 on average? How much time will I spend in state 2 on average, and so forth. So it's a probability measure. And so there is a mapping, if you think about it, from Markov chains to their stationary measures. And it turns out to be a homomorphism of the trace logic onto the Lebesgue logic. So the Lebesgue logic of probability measures that I mentioned, it is a logical structure. The trace logic is a logical structure, and the map from a Markov matrix to its stationary measure is a map from Markov chains to probability measures, and it turns out that mapping is a logic homomorphism. So what we're trying to do now is we're trying to use that logic. So we're saying let's try this. Each Markov matrix corresponds to a conscious observer, and this trace logic is giving us the relationship among all the different observers. It is, and it's a logic not simply of minimal surprise, but of no surprise in the following sense. If we take this bigger matrix as the truth, the trace then is exactly what you will see in that truth. There is no surprise. The trace is what you will see. And it turns out that when you take the bigger matrix and look at its stationary measure, and then you take the trace and look at its stationary measure, the stationary measure is of the trace is the normalized restriction of the bigger stationary measure. In other words, you get exactly the right long-term probabilities as well. So the trace logic is the logic not only of minimal surprise, but of no surprise. So it gives us a way of looking at the whole space of probabilistic processes, Markovian, as you well know, Markov chains have the limitation that they are for finite memory, for finite history, right? However, in practice, that's not a big constraint. It's very much like in Turing machines, you have the constraint that you have a finite amount of tape, on your Turing machine, but you have as much tape as you need, and so in practice, that's not a problem. So, I don't. Basically, this is a completely general kind of notion. So there's then this logic on Markov chains. I'm viewing each particular Markov matrix as just a representation of a conscious observer, because it's the simplest thing I can think of. I cannot think of anything simpler, and it has this profound logical structure on it. And so then the question becomes, and I'll shut up and let you respond. But how do we start? Then the question for me is, okay, where's the beef? Nice big logical structure. You have to give me space-time. You have to give me Minkowski space. You have to give me curved space-time, and you have to give me quantum field theory. Or the same finger can be pointed at me as I point to people who are trying to do consciousness inside space-time. Where's the beef? So I'll stop.
Oh, what do you make of that? Because when I set this interview up, what I was thinking about was many of the comments online when people talk about both your work, and they tend to make these generic comments like, okay, these are two polymaths who hide behind huge jargon, difficult to understand terms, making these broad general claims about things that we don't understand. So both of you get accused of exactly the same thing. So I figured you'd be the best guests to have a nice discussion. I'd love to hear your thoughts on this.
I'm all upset now. I didn't know that. Right. So, okay. So what I've just heard sounds remarkably similar to the commitments of the free energy principle expressed in a slightly simpler and more conventional calculus or rhetoric and set of operators. So I'm going to sort of, just in the spirit of asking whether I've understood correctly what I have heard, just see if the homologous or the analogous constructs that underwrite the free energy principle speak to the same ideas. So, this notion of a Markov chain, it's probably best just to explain what that is. So basically, what that says is that there is some assumption and commitment that there are certain states of some universe. And let's be absolutely clear about this. Even though sometimes these states are said to live in a state space, there is no, at this stage, commitment that this has any spatial attribute.
Right.
But there is a commitment that there is some ordinal lawful structure to a succession of these abstract states. And we can, it'd be really interesting to have the conversation about where do states come from. But for the moment, let's assume very much like the assumption that, that if these states exist, they must be states of consciousness. But let's assume that they exist. Then all one is saying when one has an ergodic-like or a Markov process is that there is some lawful relationship between the succession of states. Let's for simplicity call it in time. So the state of the world, this abstract world, is such that there is some lawful probabilistic mapping between the state now and the next state and the state after that. And the crucial aspect that we're talking about here is that everything I need to know in order to predict the next state is contained in the current state. So I can ignore the history of the universe, this sort of background-free universe, if I just need to predict the next state. And that basically, that sort of says that I'm somehow protected or insulated from the past because all I need to know is the current state. So in my world, this would be the simplest kind of Markov blanket, a demarcation that basically insulates me in a probabilistic sense from something else, where me in this instance is the future and the something else is the past, and the present would be, if you allow me to talk about time, would be a particular kind of interface. I use the interface deliberately because we might talk about different kinds of interfaces later on, or boundary. So so that's the key thing. And then we have this notion that we just heard about, that there is an opportunity to return to the same state at some point in the future. And if that opportunity is part of your causal physics of some abstract sort, then you can say, in some sense, that this system is agonic. And that's really important, because what that means is that there are a certain set of states, and we've heard about the ways that we can carve up states in terms of trace operators, a certain kind of trace operator and the like. There are certain states that I will revisit. And if I revisit, then they become characteristic of a subset of states which we could identify with the thing that is being that is conscious, or that exists in the sense that it has characteristic states. It has states that characterize it. There will be certain states that it keeps on returning to, right. And that's all that's meant by an agonic Markov chain. And then the question is, well, what are the interesting behaviors of these trajectories or these chains? Yes. So defined, and they already have a really interesting aspect in the sense that there will be some states that I occupy a lot, and there'll be other states that I may never visit, and that's what Don was talking about in terms of the stationary solution. So and if I was talking about this is what, and I would probably get told off for calling it this, if I was trying to use the vernacular, but this would be what 21st century classical physicists love to talk about, which is a non-equilibrium steady state distribution. So why is it non-equilibrium? Well, because if it was in equilibrium, every state could see every other state, and there'll be no way of carving the big matrix, the big state space, in the way that we just heard about. And that basically means that you're talking about equilibrium physics and the kind you talked about at school, and it would find some free energy minima that could be read as a thermodynamic free energy. That's not interesting. What is interesting is, as Donald was saying, was, we've got the big matrix, or the big process, or the big attracting set, and by attracting set I simply mean those states to which the system can return after a suitable period of time. And within this big attracting set, we can carve out certain subspaces, certain sort of parts of this, and they have relations to other parts of it. And therefore, now there become interesting questions about how much information in the sense of probability theory does this subset, this 4x4, for example, have about the rest. And just in virtue of existence of the fact that this system exists in the sense that it revisits the same kinds of states, there are some very deep implications. And I'm reading what Donald said as that once the system pursues the most likely trajectories, then there should be no surprise when we consider the state of one partition in relation to another partition. So put that into the vernacular. If we are sustainable in the sense of possessing this characteristic set of attracting states, and we keep revisiting the same kinds of states, then you become very predictable for me, and I become very predictable for you, because we are now occupying our characteristic predictable states. And there should be a calculus or a probability theory that expresses this surprise minimizing, and now from an information theoretic point of view, you could be framed as a principle of least action, where action is now the the time times the surprise or the improbability or the implausibility of being in these states. So that's what I read from that was my attempt to sort of ground Donald's waxing lyrical about traces and the like, in a way that I understood, but hopefully other people might understand. I should just slip in the kind of maths that I use would characterize these objects as something called pullback attractors. And they're really interesting objects because the attracting set of states to which the system can keep coming back to is itself a random object. And you know, and within that random object, you now have to ask some quite sort of serious questions, which I suspect have already been implicitly answered, given what we've heard, about how you carve up and how you. I can't remember the exact terminology, but it sounded to me like there was some notion of marginalization and when you do the renormalization. So, you know, we're talking about how do you carve up these states into different things, into different selves, into different, potentially conscious entities that are conscious in the sense that they are, or they can be read as inferring something about other things, and reciprocally the other things doing exactly the same. Was that I know I probably.
Yeah, so that I think is very helpful, and I'll just clarify a few things about it then. So the proposal I'm doing with this mathematics is to say, let's take consciousness as fundamental. So I'm not going to try to figure out how consciousness arises from unconscious ingredients somehow. I'm just going to say, by fiat, I start, my assumption for my scientific theory is that conscious experiences exist. So I'm assuming them, I'm not explaining them. I'm assuming that there are conscious experiences, and I'm assuming that there are probabilistic relationships among them that can be represented by Markov chains. And so that any trace, if I start with a big, trillion by trillion Markov matrix of experiences, any trace onto any subset is another consciousness, another conscious observer. So it's literally, so I'm not saying some of these are and some aren't conscious observers. I'm saying it's consciousness all the way down. And so, of course, there's no free lunch. I have to give you something. I have to show you how space-time emerges, right? So if I'm saying it's consciousness all the way down, then how do I get space-time physics? So I'll have to talk about that. But I really want to make sure my assumptions are on the board. If I were a physicalist, I would be starting off with saying my starting point is not conscious. It's like space and time and particles inside space and time, and nothing here is conscious. And I'm trying to find what properties of the interactions of particles or what patterns, like integrated information or orchestrated collapse of quantum states of microtubules or something like that, that's going to then somehow give rise to the magic of consciousness. So I'm not doing that, because so far it hasn't given us a single conscious experience that it can do. So I just decided I'm not going to be the fly in the window pane there. So I'm going the other way. I'm saying my assumptions are different. I'm starting with consciousness. That's my assumption. So I don't have to explain consciousness. I'm assuming it. Just like someone who starts with space-time doesn't explain space-time, they're assuming it, right? Then they're going to try to explain consciousness. So I'm assuming conscious experiences. And so this whole trace logic then would then be interpreted as the logic of all possible consciousnesses. So so for any set n of experiences that you want, there's something called the Markov polytope, M sub n. And that Markov polytope would literally describe all possible consciousnesses. Every element of that is a Markov matrix within there, and it would correspond to all possible n, by n consciousnesses. And then their traces, also all their traces. So, and n can go to infinity, right? So I can, that's a completely different framework. Consciousness is fundamental, and space-time will end up being, from this point of view, just a headset that certain consciousnesses use, a data structure that certain consciousnesses use as a way to interact with this infinite range of possible consciousness, many of them bigger than it, right? Any finite consciousness will have an infinite number of consciousnesses greater than it in this. And so there's one other step I have to take then before I can start to talk about space-time. And that is, I have to take the notion of a Markov matrix or Markov chain and add one little thing that's standard in Markov theory. And that is a counter. So these are called, we call them enhanced Markov chains. So every time I have a new state in my Markov dynamics, I just increase my counter by 1. So I can arbitrarily start at some like 0, and okay, now I got it. I'm seeing green now. That's 1. Well, now I'm seeing red. Okay, that's 2. Now I'm seeing blue. Okay, that's 3. So every time I change experiences, I add a counter. So this isn't time. This is just a discrete counter. It's not space-time in Einstein's sense of time or physics. It's just a discrete counter. So the question then becomes, is there any way to take Markov chains like this and get, for example, Minkowski space? And the first thing to notice, and it took me a long time to notice this, after we had the trace logic and the enhanced trace logic, it took me a long time to realize that if you, suppose I have just a Markov chain on 3 colors, red, green, and blue. And every time I get a new color, my counter is going. But now I take a trace on just, say, red and green. I don't see the blue. So for every 3 steps of the big chain, red, green, and blue, I'm only getting 2, on average, 2 steps of the red and green one. So I noticed that means its counter isn't going as fast as the counter of the big one. So whenever I have a big matrix, any of its traces, on average, will have a counter that's going slower. And as you go down the trace logic to smaller and smaller traces, you're going to be having slower and slower counters. And I thought, well, that's interesting. It's like time dilation. And I thought, could it be it all related to the time dilation that we see in special relativity, right? Where if you're on a train and you're going past me really, really quickly, and you got a clock and a meter stick, and I'm sitting at the train station, I'm just static, you're going past me on the train. If I look at Carl's clock, it looks like it's going slow to me, and his meter stick is shorter. But if Carl looks at me, it's the same. Carl thinks my clock is going slow, and my meter stick is shorter. So it's symmetric. We both think the other guy has the slower clock and the shorter meter stick. So it's really bizarre. But the question was, could that come out of the trace logic? Could it be that we could get, if we just start with only observers and nothing else, and this trace logic, could we get exactly the Lorentz transformations, the Lorentz contractions of special relativity? And it looks like yes, for a special class of Markov chains, the so-called cyclic Markov chains. So where in some sense it's deterministic. If I have like red, green, and blue, red goes to green, green goes to blue, blue goes to red, and you cycle. For those, it turns out, there is a notion of distance that you can, there are a couple notions of distance between states in a Markov chain, right? So I'm trying to, I have this time, this counter, so I'm going to somehow map that into time and space, in space-time. How do I get the distances between states? Because I have to map them into distances in space-time. And there are a couple ways to do it. I'll talk about the simplest one. There's something called slice-Dirichlet forms, and that's more complicated. I'll talk about just something called the commute time. It's that how many steps on average does it take to get from red, say, to green, and then back to red? That's the commute time between red and green. The expected number of steps of the chain to get to one and back. And it turns out that is the square of a Euclidean distance. So this is a mathematical result by Doyle and Steiner in 2017, that you can think of the commute time between pairs of states in a Markov chain as the square of a Euclidean distance between those states. So if you take that notion of Euclidean distance and you take the counter that I just mentioned as sort of the time, then it turns out that the contraction that you get in the distances, because notice that if I have red, green, and blue, on average, the commute time between red and green is going to be bigger because sometimes I go through blue, right? So it's a longer commute time. But if I have only red and green, then the commute time is less because I never go through blue. Not that I see. I never go through blue that I can see. And so my commute time is smaller. And so my distance that I'm seeing, so the distances are contracting. That's the interesting thing. Not only does the time go slower on a trace, but all the distances contract systematically on the trace because the commute times are going down. So the question is, for Einstein's special theory of relativity, those two contractions are identical. The space contraction and the time contraction are both the same Lorentz contraction. And so for most Markov chains, it's not true, right? But for the cyclic, it is true. So in other words, the idea then is that the structure of Minkowski space then comes directly from a subset of this trace logic, namely the subset of where we only look at Markov chains that are cyclic. When we go to more general Markov chains, we will start to get curved spacetimes because the counter contraction versus the commute time distance contraction will be different, and so you won't have the same Lorentz factor, and so you'll have to have a curved spacetime to represent that. So that's sort of the idea then, is that if we start only with observers and nothing else, conscious observers, and there is this canonical logical relationship among Markov chains, and therefore a canonical logical relationship among conscious observers. That's all you need. All you need is that the notion of observer and this logical relationship, and then you find that you can compute time dilations and length contractions. And for a special case of Markov chains, you get exactly the Minkowski kind of relationships. And then for others, you get the more curved. But one trick is, I mentioned that is the commute time in the Markov chains is the square of the Euclidean distance. It's not the Euclidean distance. So what we have to do then, if we're going to start with conscious dynamics and this logic, and try to get space-time in only from, we're only using consciousness and this logical relations to entirely boot up space-time, entirely, nothing else. But to do that, we're going to have to take the square root of the commute times to get the distances, and therefore we should take the square root of the clock counters to get the time in the space-time. And that means that if I'm going to actually construct a space-time in this fashion, I'm going to get two of them. I'm going to get a plus square root for distance and time, and a minus square root. And so I'm forced, because that if I'm going to construct one, why should I pick just the plus square root and why not the minus? So I'm sort of forced to construct both, and that may be the source of what physicists call CPT symmetry, charge parity time symmetry. I'm forced to do both because the reality in this model, reality is this set of consciousnesses with this trace logic, and space-time is a particular projection from that, based on just a subset of Markov chains, just the cyclic ones. And that projection requires a square root, and so I actually get two spacetimes coming out. So the spacetimes are not fundamental. They are derived from the conscious observer dynamics, and I get CPT symmetry because I have to take the square root of the deeper dynamics to get a space-time, and so I have both a positive and a negative coming out of it. So that's at top level how I'm trying then, my task, if I'm a physicalist, my task is to start with space-time and physical particles, and without any hand wave, give me the taste of mint and the smell of garlic and so forth. I mean, that's what you have to do. That's what you've set yourself up to do. I have to do the opposite. I'm starting off with the conscious experiences, then I have to give you space-time and CPT symmetry and curved space-time. And I think we can do that, whereas I don't see any way yet, and none of my brilliant colleagues have found any way to get the taste of mint from particle dynamics. So that's where I'm sort of sitting, and that we can dive into it more about how we get quantum mechanics and so forth. But that's sort of a top level, and I should stop and not have a monologue.
Carl, I'm not sure if you have anything to add to that, but I thought, you see, the way I set this up was, I figured first, let's try and understand exactly where you guys link up, because many people see your work as very similar in the sense that both of you have certain views when it comes to reality in itself, when it comes to perception, representation, illusion, interface. If I thought the title for this could be Inference versus Interface, for example, because both of you have these nice, great ideas behind this. Carl, maybe for you, we can pause what Don said and go back to it later, because the ontology can perhaps wait for now. Let's build on the science. When it comes to, let's say, does free energy minimization drive veridical representations or fitness enhancing illusions, as interface theory suggests?
Yes.
Okay.
Yes.
Then, Don, but before you, Don, and then Carl, you can answer that even more. But I was going to then say as well for Don, is your interface theory just a generative model, just like within Carl's view? So perhaps you can both play with that.
Well, I think there's very, very deep links. Absolutely.
Yeah, Carl, go ahead.
Explore that.
Let's go into that. Perhaps let's bridge these two theories together slowly and then see where they diverge.
Right. So a free energy minimizing process has a very particular meaning here, because the free energy in question does not commit to space-time or physics. This is not a thermodynamic free energy. It's much more fundamental than that, and derives from exactly the same starting point of thinking about some world or universe that can be expressed as a Markov chain. Which is, not at all controversial. Physicists of a conventional sort would start with something called the Lorentz equation. All you're saying is that an apt characterization of this universe is that there is some lawful relationship between the rate at which something changes and the state of this thing. And that lawful relationship is probabilistic, and then you add in random fluctuations, and you get fluctuation theorems, and you can go off to statistical thermodynamics, or you can express it in terms of, interestingly, the square root of the probability theory, which would lead you to quantum mechanics. So, quantum mechanics, stochastic thermodynamics, and statistical mechanics all commit to this this Markovian foundation, that there is some lawful way in which things change. And I was interested to hear that the time is, if you like, dissolved just by having this counter as a resource. I think that's an important concept, because time as we perceive it is another, really interesting sort of discussion. But to come back to the sort of the basic, the basic premises of the respective formulations and their relationship. When you can partition this set of abstract states in such a way that you can distinguish one set of states from another set of states, then you can show that should these transitions, these chains, have this ergodic property, and in particular the cyclical property that we've just heard about, if they keep revisiting states in some lawful way, some lawful sequence, then it must be the case that you can always read the set of states, which you can call, say, an observer, or the self, as holding, or you can interpret these states as parameterizing a probability density over the rest of the matrix, or the rest of, or the other, the observed. And you can write that down in continuous dynamics. So we're not talking about categorical probability or first order logic. We're talking now about density dynamics of the kind that Feynman would have talked about in terms of his pathological formulation, where you can write down, in using exactly Feynman's pathological formulation, the dynamics and the transitions and the flow through this state space that emerges or is consequent upon the ability to separate sort of the observe from the observer. And it turns out you can write it down as a gradient flow on free energy, where free energy is simply a description of the plausibility that you will be in this state or that state. So sometimes people call it self-information, sometimes call it Lagrangian, sometimes it's called surprise, or more simply it's just surprise. So I'm basically, it'll look as if I am flowing in this very abstract state space towards regions that I am most likely to occupy. So there's a really deflationary account here. It's just a description that these systems that show this sort of cyclical solenoidal kind of attracting set can be expressed probably in terms of their density dynamics as always looking as if they are flowing towards the states that they most likely are most likely to be found in. This is what, this is the definition of the attracting set. They're being slightly perturbed by these random fluctuations, by the sort of very fast things, but their flow, their dynamics constitutes the shape of their pullback attractor or their attracting sets. But the key point now is that this probability distribution pertains to the probability distribution of the interface between the observer and the observed, which means that you can also interpret it as making inferences about the observed, or at least the bits of the observed that you can see on your interface, on your screen, which I'm now reading as a Markov blanket. And I know I should just open brackets. The interface through icons is a slightly different construct, I think, because we build icons on the inside to parsimoniously sort of coarse grain and to make it very easy to interface with the Markov blanket interface. But I think that both notions speak to the same underlying calculus, the same kind of physics of sentience or inference, simply because you can now express all of these Markov chains, should they be separable in the right kind of way, as or interpret them or read them as if they were making inferences about something else. And that basically means that you can say they are performing some kind of inference. And then what I would do to make our positions entirely compatible is to say, if consciousness can be read as inference, then that's job done. I now have an internally consistent description from the point of view of this sort of foundational physics that just rests upon this Markovian assumption about the way that the sequences of states of this universe evolves, and that I can separate or carve up or tile in some way, coarse grain in some way, the sets of states. Then and if you now allow me to associate conscious processing with inference, with self-evidencing in the terminology of Jakob Hoey, then then I think that is a complete description. And then the question that we were just observing: would space and time and all of these other lovely simple explanations emerge from that? And the answer would be yes. I mean, if you're trying to find the simplest explanation, very much in the sense of minimum description length, minimizing complexity and compression we talked about before, if it is the case that the simplest explanation for everything that I see and feel in a Euclidean 3 space, should that exist, is best described with space and time as constructs, then I can have some icons, some narratives, some representations that we would call classical mechanics or Lagrangian mechanics, and that if we were really, if we had access to a telescope or a microscope, we might talk about special relativity or general relativity as the simplest explanation for our particular measurements. But these are just constructs on the inside that themselves inherit from from this interpretation of self-organization in terms of inference as consciousness or conscious inference Helmholtz would like to call it unconscious inference, but for the purposes of this conversation, I think we can allow ourselves to call it consciousness.
We're on. I think we're on the same page. I'll just say it a little bit in my language, but I think we're saying the same thing from different languages. In this Markov framework, with the trace logic, I'm basically saying that each Markov matrix represents an observer, but it's also an observed for any of its traces. So anything that is one of its traces. So the observer and observed are exactly the same structure all the way through. Any observer can also be the observed for one of its traces. And so any possible trace is another observer. And so we have this, an infinite logic of all the possible observers from the trace logic. And then there is this mapping of space-time. Then we have, in our space-time representation, we have 3 dimensions of space and 1 dimension of time. Maybe in some kind of string theory kind of approaches, they might have more dimensions, but it's, maybe 10 or 12 or something like that. When we look at the mapping from the trace logic of consciousnesses into possible space-time headsets, 3 is one of the simpler ones. We could easily talk about a mapping into a 4-dimensional or a 1,000-dimensional. So what this does is it says not only is our space-time not fundamental, it's actually conceptually one of the more trivial ones. We may not be very high in the food chain of consciousness. We may be near the bottom of the food chain because there's this simple parameter d, which is the number of spatial dimensions you can have in your headset, and we're about as low as you can go without being completely trivial. And we could easily construct higher dimensional space-time headsets with d being 1,000 or something like that. So for me, I found it sort of humbling that, I for example, here I am. I can't even imagine a 5-dimensional object. I just can't do it. I can't even imagine a 4-dimensional object. As hard as I try, and there are many cases in solving mathematical problems, if I could just visualize this thing in 4 dimensions, that would really help me just to understand, and I can't do it. And I've all of my life had this feeling like, that's really an incredible impediment. It's like really stupid that I can't do that. And now I realize in principle, there are headsets in which that wouldn't be a problem. I mean, you want to do 4-dimensional geometry? We'll just visualize it. So space-time. So before I used to think of space-time as the reality, and now I'm thinking of it as a fairly trivial and very constraining headset. I mean, it's actually impressive that we can do science with such a trivial headset that we're using. So we can imagine much more complicated headsets. And I'm not even sure that we need to be restricted to the very notion of dimension that I'm talking about. I think that we'll find that there are other classes of headsets that consciousness can use that are just utterly alien from anything that we're even thinking about right now. I just have to open up my mind to those possibilities. So instead of space-time being the final reality, and consciousness, a little emergent thing that came billions of years late, it's just the opposite. Consciousness is this incredibly rich structure. It literally has no top. The trace logic goes off to infinity. There's Markov chains can be as big as you wish. And this logic is an incredible non-Boolean logic. And space-time seems to be instead one of the most trivial headsets that can get you by. But still, that's the headset that we have to deal with in terms of science and trying to check this idea of consciousness. So I have to play within our trivial headset and say, how can I get our trivial headset out? And so one thing I do want to say is, one clean prediction of this is that I have to be able to show how each scattering process that the physicists are studying with these new positive geometries, either with Feynman diagrams or with positive geometries, I have to show, no hand wave, not only how space-time arises, but how I can get exactly gluon scattering amplitudes and so forth. So this is not I'm not taking a free pass here. I have to actually first say what structure in these Markov chains corresponds to what we call particles in space-time, right? So I have to give that kind of mapping. And then I have to ask, say, what kind of dynamics in the Markov chains then corresponds to the scattering of these particles. And I need to make absolute clean contact with everything that the high-energy theoretical physicists are doing. So one of the things that we're doing to pursue that is, it turns out that they've discovered in the last 10, 15 years that there are things called decorated permutations. So these are just permutations, but with a little twist, and we can go into the twist if people want. But I'll just say decorated permutations and just read it as permutations. But if you want, we'll go into the deeper structure. And these decorated permutations classify, strikingly, the top level structure of many particle interactions. If you write down this decorated permutation, in some cases, that's almost everything you can say about some of the simpler scattering. And for other more complicated scatterings, it captures a lot, and you have to add some other physical data to it. And so one thing we have to ask then is, okay, what do decorated permutations classify inside of Markov chains? What is it? So if decorated permutations are somehow classifying these particles and their interactions, is there some kind of way of using decorated permutations to classify substructures within a Markov matrix? And we discovered two. One is, if you have a Markov matrix which has sort of ergodic subsets, so it's a big matrix, but it's got, say, 3 different ergodic subsets, then it turns out that each one of those ergodic subsets would be something that's classified by these decorated permutations, suggesting that each ergodic subset corresponds to a separate particle. Okay? But then more generally, if you can talk about a notion of community among states in a Markov chain. So you could talk about maybe all the states are connected, but this group of states is highly connected and only very loosely connected to these states over here, and these are all highly connected, but only loosely. And you can see you can get communities with high connectivity but low, cross connectivity between. And it turns out you can also classify those with decorated permutations, something we published a couple of years ago. So the idea then is that when you start looking at the more detailed structure of Markov chains, the community structure will be something that can correspond in certain cases to the particles that physicists are seeing in particle interactions. And so that's. But then you have to go even further. They're finding, like these structures I mentioned, these positive geometries, like I'll mention the associahedron because it's one of the simplest ones. And the question would then be the volumes and facet structures and so forth of the associahedron actually encodes certain kinds of scattering processes and their probabilities, their amplitudes. So it's remarkable that you can write that down in some kind of geometry outside of space-time. So here's a hard test for our theory. If these associahedra are actually encoding for scattering processes inside space-time and they work, then I need to be able to show that these associahedra are somehow sub-polytopes of the Markov polytope that I'm working with in the trace logic. So I've got all these Markov chains. Together they form a polytope structure called the Markov polytope. And I have to be able to take all these positive geometries and embed them into the Markov polytope. And I think we can. So I think I'm working on that right now. I think that we can actually embed associahedra into Markov polytopes in a way that the facets line up, and we'll actually be able to give exact matrices with exact probabilities on each entry of the matrix that correspond to literal scattering processes inside space-time. So the idea is, again, to go beyond hand waves to actually show in great rigorous detail that the positive geometries that the high-energy theoretical physicists are finding outside of space-time are actually subgeometries of the trace logic, the Markov polytope and the trace logic. So again, someone might think, well, it's very easy for you to talk about consciousness being fundamental outside of space-time, but where's the test? I'm saying that there are going to be all sorts of hard as nails tests that we have to pass for this thing to be to be accepted. And so it's not beyond disconfirmation by mathematical and empirical tests.
Oh, what do you think about that? Except for Don's test that he's given, do you find that there are any other ways one could attempt to falsify this or attempt to structure this within a physicalist framework?
Yeah, that's a difficult question for me to answer. Again, I look at everything through the lens of the free energy principle, and in physics, a principle is a method. So it's not a theory. It's a method, and you can only apply a method. So you can't falsify the free energy principle in the same sense you couldn't falsify a t-test or Hamilton's principle of least action. It just, it's the wrong. It doesn't have the attribute of falsifiability. It should, though, be applicable. And therefore, I think there is a question of what do you apply it? And generally speaking, what happens is that people apply it to a particular generative model that you mentioned earlier on. And if you're now trying to explain the behavior of some particle, person, or population as doing this kind of unconscious or conscious inference under a generative model with the right kind of icons on the inside, suitably and usually quite deeply structured in a nested way, then that then becomes a theory. So you have a theory that this particle, person, or population can be described as if they were acting under this kind of generative model. And then based upon your measurements of this particle, person, or population, you can then make an inference to test your theory. And then I wouldn't use falsification is very much a sort of, I thought we were in the post-Popperian era. So I don't really talk to
that's my bad choice of words.
Yeah, but you can certainly compare the likelihood of this theory in relation to that theory in explaining or accounting for the observed behavior of the observed or the particles that we were just talking about. So in my world, this immunity structure and this tiling of the everything in terms of the large matrix, as it were, is a process. Some people refer to it as Markov blanket discovery. It's basically discovering the conditional independencies or the lack of couplings or connections that define a particular community, and in particular, when written down in terms of Markov blankets, that definition being that there's a condition, there are a set of intervening states upon which you condition to render the observed and the observer conditionally independent. So they only talk through the interface, which is the boundary or the. But of course, there can be a large number of ways of carving up things into observers or particles. And possibly, well, I'm not saying uncountably large number, but certainly a large number of ways of doing that. Because once you've done that, you can then have particles of particles, and I think that's what Don was alluding to, that there is the scale invariant aspect to the way that you do this carving, and that the relationship between one scale and another scale now starts to become really interesting and starts to matter. And I suspect that's what in one sense what Don was talking about in terms of one trace entailing entailing another. There are lawful relationships between a fine-grained carving into particles and a coarse-grained one. Just to sort of, I forgot what we were talking about. Sorry, I forgot what the question was, but I was intrigued. Can I just pose it did strike me a lot of what you said would fit also very well. There are lots of other sort of there are things like category theory that you could bring to the table. There are things like the renormalization group you could bring to the table. There are things like information geometries and statistical manifolds that gauge theories, or and all of them I think would be a natural space in which to explain what you've been explaining to certain kinds of mathematicians or physicists or applied mathematicians. But I did notice you're really focused on satisfying high energy physicists at the quantum level. And I'm just asking you rather cheekily, that's not something that I would have expected. I would have expected you to go for trying to derive or show the emergence from the first principle. Observers are there. What are they observing, and what defines them as observers? Show from that the emergence of the things that you were talking about, such as the taste of garlic, or even perhaps even more elementally, why we seem to be so committed in many of the natural sciences to a Euclidean free space. I have to say I'm not. Once you start to get into tensor networks and you start to think about state spaces, the notion that there are only three states, or you have to deal with it dissolves. And I have to say, I mean, given your previous work, say on face perception, you could quite easily conceive of a 30-dimensional object. Given that face requires 30 sort of eigenvariates to specify. So my question is a bit cheeky. Why do you think you need to convince high energy physicists about scattering and the emergence of certain geometries? Is that the right scale to do this?
That's a great question. Of course, I've got a number of things I need to deal with, right, to have this scientific theory be taken seriously. So and that's one of them, but maybe not. I mean, you're pointing to others that could be even more interesting to my cognitive science colleagues, for example. And the idea, for example, of how something complicated like the structure of a face is an experience, but it's made of little experiences, little patches of color and gradients and so forth. How do you put that all together to make this new coherent experience of a face and so forth? And I'm very, very much interested in that aspect of it as well. I've got a book called Observer Mechanics, where I am my colleagues Chetan Prakash and Bruce Bennett go into this quite a bit. So I do spend a lot of time there looking at how, if I assume I have certain kinds of conscious experiences, how can I construct these bigger conscious experiences that are bigger tokens and get a hierarchy in that direction? And that's very, very important. So I am doing that. The reason I'm focusing on the high energy theoretical physics connection is, in some sense, because that's the hardest, right? And that's the one. If you can't do that, then I don't care how well you put together other conscious experiences out of little conscious experiences. If you can't give me space-time, then you don't have anything. So it's really the do or die test for it. I already know that I can build, and we've known that we can take smaller conscious experiences and build bigger conscious experience. That's not a trial by fire for my theory. That we can do, but the trial by fire is claiming that consciousness is fundamental, not space-time. Right? That's the big one, because that's the one that most people are going to say, I get off the train. Space-time is fundamental. Put it this way. The idea that consciousness is fundamental has been around in spiritual traditions for thousands of years. Right? This is not a new idea. And what technology has that given us? None. All of our technology starts with the assumption that space-time is fundamental, and Maxwell's equations and quantum field theory and so forth. These are all defined over space-time. All of our technology assumes space-time. The idea that consciousness is fundamental has given us nothing in terms of technology. So if you're a betting person, you're going to bet long and hard against the consciousness fundamental point of view, and bet really long on the space-time is fundamental, because it works. So for me to row against that tide, I've got to face that obvious and natural objection. It's an objection that occurs to me just automatically. It's like, give me the beef. If you're really starting with consciousness and you're saying that that's more fundamental than space-time, then show me something that you can build that you couldn't build if you started with space-time. So for me to do that, I first have to be able to show how space-time is a special little structure from the larger trace logic of conscious agents, for example. And then once I can show you how space-time arises, that's not enough. I then have to show you something new. I need to be able to show you a new technology that arises from a theory that's outside of space-time. So the analogy I would put here is that, I mean, if space-time is just a headset, we've been playing this VR game, right? We've been playing this wonderful VR game inside our virtual headset of space-time. And we've become wizards. But science has really just been not studying reality as it is. Science has been studying a particular headset. And so space-time physics has been, according to my view, not the study of reality as it is. It's been us inside of a particular VR game studying that game, not knowing that there's a supercomputer outside for which this is a trivial representation that's running the game. So we have to, if we take consciousness as fundamental and say this is a step outside the headset, then the natural objection is, okay, then give me at least the first layer of software outside the headset. I want to see that first layer of software. And if you actually do get that layer of software, say for a VR game, suppose the person is a wizard in Grand Theft Auto, but I know I'm a geek that wrote the software, then I can do miracles in the game because I control the software. I can make his car disappear. I can make this car go 1,000 miles in 1 second. So if that's the technology that I'm thinking I need to be able to show for this kind of theory to be taken seriously. So I need to be able to show first that I can get the positive geometries that the high energy physicists are finding, to show that I really can see how space-time is constructed as a headset. And then I need to show, here's a new technology that you could not construct only within the tools of space-time. So, for example, the speed of light is the speed limit inside space-time. But if I think about it, that there is a maximum speed inside a particular Markov chain, and it is the cycle. The end cycle is the fastest you can go from state to state. So there is a speed limit inside Markov chains. But if I have a big Markov chain on a lot of states, and then I have a small Markov chain on a subset of it, so a little trace, I'll call that the visible. So this little guy only has the visible set of states, but there's a whole set of hidden states that he can't see. If I'm operating on the big set with the big Markov chain, I can see the visible and all the hidden states, I have lots of time that the little guy can't see. His counter is going much slower than mine. So for 1 second of his time, I could have 1,000 years on a bigger trace, right? So and so I could do things in his little VR headset, his little space-time, that would look like miracles to him. I could put something here and have it, put an object there and have it move at Mach 40 instantly, because I'm not stuck in his space-time. I'm operating something outside on hidden states for that person. So the very fact that if I can do this, that I can first show how his headset can be constructed as a special space-time, and then I've got access to all these states that are outside, I should be able to then do miracles inside of his space-time, things that you just can't, that seem to disobey the laws of physics in his headset, because I'm not stuck in his headset. I have hidden states that I can work. So that's why I'm really going after the high energy theoretical physics stuff, is that I am a cognitive scientist. I'm very, very interested in how I start with smaller low-level perceptions and build more complicated things like objects and faces and so forth. Very, very interesting. I've spent a lot of time on that. But I realized that's not going to move the needle for any hard-nosed physicalist scientist. That's just not going to move the needle. The only thing that's going to move the needle is show me exactly how you get all the scattering amplitudes and show me exactly a new technology that you can't do inside of normal physics. So that's why I'm headed for that, because it's I'm a hard-nosed scientist myself. I really can't believe my own theory until I can do that, right? If I can't give the software, then there's no reason for me to believe my own theory. So I really have to go after it that way. I did want to just mention one thing. We really agree on this, the importance of minimizing surprise and free energy and so forth. And I just really wanted to emphasize that the trace logic really is the logic of minimal surprise. It really is saying, in this framework of consciousness, these are the guardrails. This structure is the guardrails, which says how surprise is distributed across the thing, and the logic of minimizing surprise. That seems to be at the very, very core of this theory of consciousness, is this trace logic. And so for me, it's not like you've focused on this for many, many years. And I think it's the right focus, and it somehow is turning out in our mathematics to be like the central object that is governing the whole thing, is minimizing surprise. So
with that in mind, Don, what type of questions would you have for Karl regarding your work, trying to sort of tie these concepts together, bring your work a little bit more fine-tuned? Perhaps Karl could give you some great advice.
Well, absolutely. I would say this. Obviously, the stuff that I'm doing is way out of the mainstream. No doubt about it. What kinds of projects do you think I should, or tasks I should try to take on, things I should try to show or prove? In addition, I mean, I'm doing all this stuff on high energy physics, but other things in either consciousness science or cognitive science that you think would be really important projects that would be do or die tests of the path that I'm taking. I think that's really important for me. I mean, is there some, for example, task that you think you might see as a serious problem that maybe this couldn't do, this approach couldn't do? That would be very helpful.
Yeah, it would be arrogant of me to assume that I can tell you what are going to be challenging or useful proof of principles. But one way of answering that is to look at what the community currently want. And what they want is the next big thing in intelligence, which I think we could read as synonymous with consciousness. What are the technologies? What is the calculus? What are the principles that underwrite what what some people call AGI, some people superintelligence, some people call universal intelligence, some people call natural intelligence. And that basically reduces to exactly the question that you're posing yourself, is, what is the fundamental nature of the self as part of a universe? And I think the proof of the pudding, of course, is going to be exactly the proof of principle that people are currently waiting for, which is, what's going to replace large language models, what's going to show true reasoning, true understanding of their world, with the right kinds of generative models and right kinds of icons, liberated from a Euclidean 3 space. If I have to just a little nod, I often look at 3 spaces as an irritating constraint, especially in talking to colleagues, because I work a lot with something called the Helmholtz-Hodge decomposition, which is basically a way of decomposing that cyclical flow around the states you were talking about into one that is on the cycle and one that is drawn away from the orbit or the cycle. And it's fairly trivial just to sort of decompose them into, and that's really important from the point of view of classical physics of self-organization, because what we're talking about is breaking detailed balance inducing the kind of tiny reversibility that we see in biotic self-organization. But the Helmholtz decomposition was originally introduced just for the free space fluid mechanics. So I always find myself being corrected. Oh, that's not the Helmholtz decomposition. I say yes. All right then. Yeah, generalized to an arbitrary number of dimensions. So for me, I can empathize totally with the sort of the orthodoxy it has to be in a 4D setting, or framed in a 4D background. Anyway, close brackets. So I don't know, but what I find myself doing is applying what I think are the right kinds of principles to particular problems to demonstrate a proof of principle, to make artifacts that can do this or can do that. Now, what kind of things they are doing, of course, is depends upon what you would consider to be a sufficient proof of principle. You want to reproduce the statistics of scattering of small particles. I have to say that there's nothing quite fundamental about that. That's just observational physics. So you could apply, I think, the same. Just reading the answer to my previous question as you want to supply evidence that you think other people will take seriously. I think it's useful just to think about that, because now you're in the game of theory of mind, and you're trying to guess, how will I convince this people, and probably more importantly, who do I want to convince? So we're in the game of really sort of providing evidence that will satisfy somebody else, and what kinds of evidence would you like? I mean, things that could drive cars with true sentience, I think, would be nice. Things that would play the same role as my pet dog in terms of entertaining my children or comforting me in some way. That, I think, that kind of sentient or conscious artifact that was built or engineered based upon the right kinds of principles would be very convincing evidence.
That's a very good point, Karl, and I agree with you 100%. And I mean, as you well know, so I'm not saying this for your benefit, but just for the broader audience, that there is a deep connection to the extent that I'm surprised by my actions. I'm not very smart. If every time I pick up my glass, it falls to the floor, every time I try to button my shirt, I rip my shirt, well, I'm surprised, and I'm not very bright. So there's more to intelligence than minimizing surprise, but there's not less. Minimizing surprise is really a key aspect of intelligence. And so, and I know you're already working yourself on AI from this new point of view, past large language models, and it's a worthy challenge. I would agree that would be the trace logic, since it is the logic of the guardrails of minimizing surprise. That's what it is. Would be an interesting framework for AI, and there's an interesting. So I'll put down an interesting technical question in terms of AI in this framework. Suppose I have two different Markov matrices that establish some that I built that are having some intelligent function that I really like. So they're intelligent, and I've really worked hard, and they're doing the intelligence that I want, and they're compatible. So I've got this matrix that I really worked hard and I got it. I got this matrix I really worked hard, I got it. And it turns out that where they overlap, the states where they overlap, they are compatible, right? And so now I've got the task. I would like to get a new, bigger intelligence that encapsulates both the separate intelligences, but also all the connections between their intelligences. In other words, I want the right natural generalization of this to the higher level intelligence. Well, now I've got a new problem. I have to now work on this bigger thing. But with the trace logic, no. I've already got these. All I have to do is take their join in the trace logic. And if I have an algorithm for computing the join, then I don't have to do the work of trying to figure out what is the bigger intelligence of which these two are the traces. I can compute it. So that's one interesting way where the trace logic could come in handy here is basically it would allow you to assemble little modules and then begin to have an intelligence that combines them without having to start de novo from it. Now, what may happen in doing this is maybe they don't strictly overlap correctly, right? Maybe they have some small, the probabilities are off, so they don't really exactly line up where they meet. Then the question would be, are there algorithms based on the trace logic that can sort of minimize that and in the right way minimize the wrong overlap to change the intelligence the minimal amount so that they agree on the overlap, and then you could compute the bigger one, for example. But we have it's easy to compute the meat, as it turns out, of any two, if it exists. It's easy to compute that. There's no computational problem there. The join, I'm working with a brilliant mathematician, Chetan Prakash. I've worked with him for 40 plus years. And Chetan has come up with a formula for the join of the trace logic in special cases. So he's got a nice closed form formula for it. But it's not general. So if I have, I forget exactly where it falls apart, but I think if we have like 3 or more states of overlap, we don't have a closed form solution for it. And we don't know if there is one or not. That's an open technical problem right now in the trace logic. If there is a closed form, then this would actually be an incredibly powerful way to build AI systems where we build the smart components, get them to agree as much as possible on their overlap, and then just use the trace logic computation itself to expand the intelligence upward. But it's also possible that there is no closed form. So, I mean, we just don't know. There may not be a closed form in general. And it turns out that there may be in this logic, this is something Chetan was saying to me the other day. And again, I'm not saying that he knows for sure, but I've looked at it and I think he's probably right, that for many of these Markov matrices that are compatible, so that where they have a well-defined meet, they might not have a unique upper bound. They might not have a least upper bound. They might have a whole 1 or 2 dimensional or n-dimensional subset of or space of minimal upper bounds. So in other words, there might not be a unique matrix above them in the trace logic that traces down to them. There could be a big, large parameter family of matrices, all of which have these minimal surprise traces onto these two. In which case, that's actually pretty interesting in terms of building an AI, because it means that minimizing surprise isn't the only thing that we could have in our architecture. The trace logic gives us that guardrail. You're always on a minimal surprise path, and that's what you want at a minimum. But we could also then start doing something else. In all those different matrices, all of which are minimal upper bounds of these two lower matrices, but none of them is the least upper bound, we could then say, I want to choose the one that has the minimum entropy rate, or maximum entropy rate, say, the maximum entropy rate. So that would be, in other words, we may be able to design AIs where the guardrail of minimum surprise is there automatically from the trace logic, and then we start adding other factors that we want to build into the AI, like maximizing entropy rate or something else that we could. So I do see this as an interesting direction that we could go with it. In terms of, life is short and time is limited. My strategy has been, there are geniuses over there in the high energy theoretical physics area. If I got them interested in this, I wouldn't be able to keep up. As soon as they started working on this stuff, I would just kick back because I might not even be able to read their papers. on my own work. So and that's what I want. I really want. I've seen smart people that are so smart that I don't know how smart they are, and I know as soon as they start working on this, I can just kick back and relax and watch the thing take off. So that's one reason why I'm also going after that crew. Is I think that they would then just hit the accelerator and take it off. Whereas I'm going at a very pedestrian Hoffman level pace.
Yeah, well, that's a comment.
So you could
So, no, yeah, no, if I had to convince somebody, theoretical physicists would be the people I choose to convince. That's absolutely right.
That's right, because they're brilliant. They're absolutely brilliant, and they have the right tools.
Yes. I think that's they have the best icons. So just one little question. In terms of surprise minimization, and I was really interested in your discussion about the tractability in terms of the degree of overlap. It did remind me, of course, of Richard Feynman's PhD, where he introduced variational free energy to solve exactly the intractable marginalization required to estimate the actual surprise read as a marginal or negative, not marginal likelihood. But it did strike me, if you've got that basic technology at the quantum level, then you could start to pursue sample efficiency and the same kind of objectives and proofs of principle that quantum supremacy aims for. If you can show that you can do some kind of elemental computation really, really quickly, or with orders of magnitude more sample efficiency, that would be a really practical proof of principle that inherits directly from the scale at which you're currently working, that would engage quantum physicists and also quantum information theorists and quantum computer experts. So,
I agree, and it's I haven't actually at all mentioned how quantum theory fits into this whole trace logic framework at all. I've only talked about Einstein's classical spacetimes, but not the quantum aspect of it. And Chetan discovered a very interesting aspect of it. If we look at the eigenfunctions, the harmonic functions of these enhanced Markov chains. So I have a Markov chain, but I have this counter, and so I can take that Markov chain with a counter and look at its so-called harmonic functions. And it turns out that the harmonic functions are identical in form to the quantum wave functions of free particles. Exactly. They're the same thing. The idea that we're proposing is that quantum theory is describing, well, first I should say, notice that I've not talked about like quantum probabilities. Right? I've been using just classical probability theory. So one obvious objection to my whole approach is to say, look, Hoffman, you're trying to get a fundamental theory of consciousness outside of space-time using only classical probability. What about quantum probability? You're not using all the tools that are available to you. And so why are you sticking yourself with this smaller set of tools? And our idea is that the quantum laws and quantum mechanics is only a description of the asymptotic behavior of the Markovian dynamics of observers that we're dealing with. So that's going to be and we have to then show that we can get all of the quantum probabilities and quantum interference things from our trace logic with classical probabilities. So that's the claim, that quantum probability is not more fundamental than the classical, that all of quantum behavior is really, the reason it's sort of mysterious is that it's not the fundamental behavior, it's only the harmonic, the asymptotic behavior of a much deeper system that we can actually describe with classical probabilities. So and there are things we're looking at called Berezin integrals that allow us to use just the classical probability and the structure of hidden states in the trace logic to actually show that the imaginary numbers that appear in quantum computations of probability are really, those imaginaries are really pointing to a deeper structure of barrows and integrals and the geometric algebra approach of just these classical states where some of them are hidden. And the imaginary is telling you basically how to handle the states that are visible versus the ones that are hidden. So there's a lot that we have to do on that, but it's going to be, the idea is that quantum theory is not fundamental. And by the way, I should say, this is not just a cognitive scientist saying this. Now I'm actually quoting Nima Arkani Hamed, who says that space-time and quantum mechanics together are not fundamental. He's saying we have to go outside of space-time and quantum theory. So, for example, when he says there's no locality and there's no unitarity, that's when he's saying quantum mechanics is not fundamental. So this is, in some sense, I'm not on thin ice when I say this. I'm just parroting what high energy theoretical physicists at the high energy level are saying, that not only is space-time doomed, but quantum theory is doomed as being fundamental. And so we have to actually, from our point of view, that's another burden that I haven't mentioned that we have to do. Not only do we have to get Einstein's classical spacetimes out of it, we have to show that quantum theory and all quantum probabilities and non-localities and all the things that we get in quantum theory really arises from the trace logic itself. That is not fundamental, or we're wrong. So that's another thing on our bucket list, is we have to show that quantum theory only describes the harmonic functions or some asymptotic behavior of our approach. So it's everywhere I turn, there are big asks.
Carl, before you go into that quantum realm, perhaps in order to sort of give an idea of where your view comes from, or Don, is free energy minimization equivalent to fitness maximization? And is phenomenology necessary or emergent from non-conscious principles? And thereafter, I want to move on to time before we move on to quantum mechanics.
Is that for me, or is that
for Carl? Oh, so
for Carl. Yeah.
I just want to get an idea where your views align, and then thereafter quantum thought.
Yes. So don't let me forget to make a comment about the quantum aspects. But that's a great question in itself. Yeah. So just going to unpack the technical meaning of the terms that we've been using. Surprise is being used in a very specific sense here. If you're in information theory, it would be called self-information. If you were doing probability theory, it's just the negative log probability of something. So it's the implausibility of something. And it's a really important quantity, because if you want to characterize anything in terms of the kind of states that it could occupy, you just have to label every possible state with how plausible is it this kind of thing will be found in this state. And this is exactly a specification of this attracting set that we were talking about before. And that basically means that you can define things in terms of surprisal, and then you ask yourself, okay, how would things behave? Well, things will behave in a way that renders them recognizable as having characteristic states, and they behave in the most likely way that those kinds of things will behave. So almost tautologically, what you are saying is that things will organize or behave in a way that minimizes their surprisal. Why? Because they behave in the most likely way they behave. What is the most likely way they behave from the point of view of surprisal? It's a negative log likelihood of the way they behave. So there's a deep tautology here. So it doesn't surprise me to hear that the foundation of the trace calculus is a surprisal minimization. It can be no other way.
Yes.
You can also articulate exactly the same thing from the point of view of theoretical biology and evolution and natural selection. So you see exactly the same tautology here. Why is this thing adaptively fit? Well, because it fits adaptively to this environment. How do I know it's adaptively fit? Well, it's the most likely thing I'll find there. Articulated, it behaves in a way which blah, blah, blah. Well, what's good behavior? Well, it's a behavior that means that it survives in this environment. So there's this deep tautology. And of course, you can dissolve, or not dissolve, but you can render the equivalent tautological, almost stipulatively definitional characterization of surprise minimization and natural selection synonymous, just by noticing that adaptive fitness is basically a measure of the likelihood you will find this phenotype in this niche. So if you're maximizing your adaptive fitness, you're maximizing the log of the probability of this phenotype given this niche. What's that? It's a negative surprisal. It's also called the marginal likelihood. It's also in statistics called the model evidence. So the probability of some observations, say observing a phenotype in this niche or some data, given a model of those, usually a generative model of those data, is also the evidence for that model. So if under this model, I find these data very unsurprising and and all I'm saying is they're very, very likely under this particular model, which means now I can compare the likelihood of this model produced these data with the likelihood that an alternative model, i.e. hypothesis, could have produced these data. So this is Bayesian model comparison. But notice what we've done. We're using the surprise to do the Bayesian model comparison. If I'm going to select one hypothesis over another one, say a phenotype in natural selection, then I'm doing Bayesian model selection based upon usually a variational free energy bound on the surprise. Because we can compute the bound, we can't usually compute the surprise. Hence my question before about reference to Richard Feynman's work. So what we now have is a really simple view of natural selection, of nature's way of doing Bayesian model selection, which just means that it looks as if nature is trying to infer what are the phenotypes that fit into this environment. So it's just a process of Bayesian belief updating or Bayesian model selection, trying to work out what is the most likely thing I will find in this environment. Because things get really interesting when coming back to Don's earlier observations about communities, when the environment is also composed of things that are being selected. And then you get sort of interesting questions. Are they the same kinds of things? Is it a homogeneous environment? Or do we have codependencies when we co-construct these environments? And again, to issues of niche construction and the way that one kind of observer or one kind of phenotype basically provides evidence for another kind of phenotype, and all sorts of interesting questions. But at its heart, these are just free energy or surprise minimizing processes. Why? Because things definitionally change in a way that is most likely for the kind of thing that they are. It is as simple as that. So I think there really is a very deep connection there. And just to gracefully get back to quantum physics with the way you would possibly notice, if it is all about describing things that exist in the sense that they will change in a way that is most likely given the kind of thing that they are, then that means that it is surprise or probability, classical probability, that is the key metric here. It is the information geometry that matters. It's got nothing to do with space-time or special relativity. It's the information geometry that is defined by the surprise or the marginal likelihood. And in that sense, the square root, the complex square root of the probability, which is known as a probability amplitude in quantum physics, is a consequence of that. So, Don, I thought you'd solve the quantum mechanics problem because you were talking about your positive and negative square roots. So all you have to do is to take the classical probability and say, I'm just going to arbitrarily factorize it into a positive and negative square root, and I'm going to treat those as probability amplitudes. And then you can derive all quantum mechanics. Well, I'd say you can. It would be, I put it to you as another way of convincing your friends in energy, in high energy physics. If you can derive the time-independent Schrodinger wave equation from the trace operator, which I'm absolutely sure you can, because if it's surprise minimizing, it must be marginal likelihood maximizing, and therefore it must succumb to a pathetical formulation. If you can do that, you can show that there is a mapping between the formulation in terms of surprise minimizing operators and all the logic that ensues, then you can derive from that just by taking the complex root of the surprise or the classical probability to show that this is equivalent to the solution to the solution. The free and surprisal minimizing solution is the Schrodinger wave, time-independent Schrodinger wave equation, and then from that you've got all quantum mechanics.
I think you're right, and it's interesting because when we look at the way that the trace logic works, when I take a big matrix on a lot of states and I trace it onto a subset of states, what I have to do is for all the visible states, the new visible states, and then there are all these hidden states. What I have to do is for each transition that's visible, I have to compute all possible excursions into the hidden states, and there's an infinite number of them. So the trace logic itself, even to compute the trace, you're assuming that you're looking at the infinite number of paths, all of them, and taking account of all the infinite number of paths in the hidden states that you can't see to get the probabilities that you've got in your visible trace. And so that's right there, the very essence of what's going on in quantum mechanics. You're looking at all possible paths and so forth. So I completely agree that it should be pretty straightforward to show that quantum mechanics and therefore quantum probabilities fall out from this as sort of just the asymptotic description of what we're doing here.
Yeah, you're doing a sort of another kind of strange inversion, sort of akin to Dan Dennett's notion. You've done the strange inversion. Let's go from consciousness to physics, whereas most people would go from physical systems to consciousness. Now, I think there's another strange inversion lurking here, which I think is a completely correct one, which is going from classical probability to quantum mechanics. Yeah, you don't need the Bloom rule. You can do everything in the pathological classical probability and then just arbitrarily say, okay, so I can use Fourier transforms. I'm going to actually just take the complex root of my probability distribution, and then you have quantum mechanics and all the nice linear operators that you can enjoy in that context. The final point, though, just for people who don't know the background to the free energy in and of itself. So free energy is an approximation to or a bound on surprise. It's not in and of itself surprise. So the way that you were describing the problem to understand and gesticulating with the infinite number of paths, of course, this is exactly what Richard Feynman tried to solve. He had to work out what's the probability of an uncountable number of paths from the initial to the final state of a particle. Of course, you can't do it. It's computationally intractable. It cannot be physically computed, but you can induce a bound on that probability. And that, of course, is the variation of free energy. So it was exactly this problem that brought free energy to the table within Feynman's pathological formulation of quantum electrodynamics. Exactly.
Yeah, I agree that the connections are deep and beautiful there. It turns out in the case of the just Markov chain version of it, when you look at the trace, they found a closed form solution for the trace. So suppose I have the states, I'll call them, the total set of states is S. That's the total set of states. And there are a subset of S is V, the visible states. And the other is H, the hidden states, okay? There's actually a closed form formula that says, given a matrix on S, the big, so S is V plus H, so it's visible on the hidden states. How do you get the trace onto V? And it's very, very simple. It's so call the matrix P. So the big matrix on on all of the states is P, and you just take P restricted to V, right? So the VV subset of P plus the restriction, I'll call it P restricted to VH, that little part of the matrix, times the quantity I minus P restricted to HH, that quantity inverse, times PHV. That's it. It's a closed form formula. So you can actually, that I minus PHH inverse, the whole thing inverse, is, it turns out, the infinite sum. That captures the infinite sum through all the possible paths. And so it gives you, so there is a way to, in general, that you can do, maybe there are some cases where you can't, but in general, you can do it as a closed form computation. So we actually compute the trace really quickly. We don't have to do the infinite path kind of thing because it's all there in the formula. But there was another thing you mentioned, which is about the evolution and the phenotypes and the implications of all this for that. And one of the interesting phenotypes, of course, is the sensory systems and the relationship of the sensory systems to reality. In other words, are the sensory phenotypes veridical? Do they give you veridical perceptions of reality as it is? And the work that I've done with Chetan Prakash and some graduate students, Justin Mark and Brian Marion and others, and I should, Manish Singh, others, Robert Prentner. I've got a lot of collaborators. So this is not just Hoffman, a lot of collaborators. What we've found in a lot of our work is that you can ask a clean technical question. Now I'll get out of the consciousness first framework, and I'll just go back to standard evolutionary game theory. Just go to the standard tools, John Maynard Smith's representation of Darwin's theory. And we can ask a clean technical question. What is the probability that evolution would shape any sensory system to see any aspect of objective reality? That's a nice, clean technical question. And I think most people would say, there's a good chance, right? I think I see reality. I'm seeing it pretty. In fact, the reason I don't die is because I'm seeing reality as it is. I mean, evolution gave me a nice, clean, true picture of reality, and that's why I live. And so the answer is very, very high chance that evolution shaped us to see reality as it is. That's most people's intuition. Is sort of like, duh. I mean, of course it does. And when you do the math, it's very, very different. And the argument is disarmingly simple. Evolution places no a priori restriction on the payoff functions that you can consider in evolution. So in evolutionary, as you well know, but I'll just say it anyway, for evolutionary game theory, you have to specify a payoff function, right? And the payoff function says, if you have this organism in this state, in this context, and it takes this action, what are the payoffs, for that organism? So it's a function that takes an organism, state, and action, and gives you a number for the payoff. The likelihood that you will survive long enough to reproduce is the payoff. So evolutionary game theory puts no restriction on the admissible payoff functions. So when we ask ourselves, what is the probability that evolution shapes sensory systems to see reality as it is, we have to consider all possible payoff functions. And then we can ask ourselves the technical question. For evolution to shape a sensory system to see a true structure in the world, it has to be guided by a payoff function which is homomorphic, which is a homomorphism of that structure. If the payoff function doesn't have any notion of that structure, it can't possibly shape you to perceive that structure. So you have to then ask yourself, okay, for any structure in the world, like a total order or metric or whatever it might be, what is the probability that the payoff function that's guiding your evolution is a homomorphism of that structure, and so that you could be evolved to perceive that structure. And we've done 4 or 5 cases directly and computed them. Again, this is now a real mathematician, not Hoffman, Chetan Prakash. And the answer is, the probability is in the limit as the number of states in the world goes to infinity, precisely 0. The probability is precisely 0 that any organism has been shaped by evolution to see any aspect of objective reality veridically. 0. So, and for most people, this is, a completely counterintuitive result. The assumption is, of how can that be? We're surviving. We must see the truth if we're surviving. How could you survive if you don't see the truth? So that's the natural objection.
And in fact, this is Don. This is partly how I wanted to start off this conversation, was because both of you fundamentally claim perception is sort of illusory from an interface perception and from an inference perception. So Karl, I'm curious to know how you respond to that, because while you both mean that we infer different realities from the actual reality, there's both a case against reality. How do you feel about the fact that there's a possibility or probability of 0 veridicality to reality? Do you agree? And if not, why not?
I think the argument was that there's a 0 probability that we will have evolved to sense a reality should it be out there. I've got to be careful how I answer that, because it depends who I'm talking to and which friend I'm going to offend the least or the most. So don't do Jakob Howie would be one answer, but Andy Clark would be another answer, and so on and so forth, and Neil and whatever. But what I generally say is, I think you can sort of be quite candid about this, and until you start to take Helmholtz seriously, and the reason I sort of phrase it like that is that I think Helmholtz brought an inactive aspect to, I would argue conscious, but he would argue unconscious inference. So it was his sort of work. It's not just sense making, but also how you actively gather the data to resolve your surprise, to make yourself behave in the most likely way that things like you behave, which is just basically what you will be selected for, if you're allowed to behave in that kind of way. And that suggests to me that there has to be a kind of reality out there to be sampled by our sensorium or our sensory organs. So that suggests that, from the point of view of carving up a large Markov chain or state space, either in terms of tiles or communities or in terms of Markov blanket partitions, it does mean you're presupposing, if you want to tell this story, that there's something that is like to be a particular particle, but you are embedded in something out there which is your reality. Otherwise the maths doesn't make any sense. But it's all in the relationship between the particle, the self, the observer, and everything else, the observed, that sort of defines the likelihood of finding this phenotype in this niche. You have to have a niche before you can have, define the likelihood of it. There always has to be a context. And we've heard about the different ways in which the, Don's articulated that context in terms of looking at sort of smaller versus bigger parts of say, a matrix. For me, it would be that, it would be truly relational in a sort of Ravelli-like sense, that it, this surprisal, if you remember before, it is just based upon the probability of these sensory impressions or these data or these exchanges with something, given my model of that something. So notice it's a function of something that has to be out there. It's not you, it's the data. So there has to be some, if you like, metaphysical reality even if it's just the data that you are making sense of or that define your marginal likelihood. The marginal bit, I should explain, this is a bit of statistical jargon. It means averaging away in exactly the way that we were talking about before, in terms of the uncountable number of paths that I could, to get a probability distribution over it. What I need to do once I got a probability distribution over everything, I need to average away my uncertainty to winnow down on one thing. So perhaps it's a 4x4 tile with a very, very large matrix. So I have to, in that marginalization, I have to integrate away all the states that I cannot currently see. So that's why people talk about surprise or model evidence as a marginal likelihood. So yeah, when we talk about the likelihood of finding this kind of spider in this kind of forest, we are not terribly interested in all the microscopic states of the spider that characterize the phenotype. We've coarse-grained it. It's just that. It's just a spider of that sort. That's yeah. Again, I forgot the question. I got carried away again. That's getting too excited and tired.
But overall, then, Carl, would you agree that evolution would do that? Do you think there's a chance it would do that? Give us a probability of understanding reality that low, or do you feel like
yeah. Well, I mean, I think. Yeah, I mean, remember, from my point of view, evolution is just a surprise minimizing process. So there is no objective function. There is no game theoretic payoff at all, other than the surprise. So Donald actually said this out loud. He said, the likelihood I'm hanging around to reproduce, it's just a marginal likelihood. There is no reward function. There is no value function selection problem. It's all about surprise. It's just that you have to read surprise carefully in this context. Surprise is just, I repeat, the likelihood that I will be found in this environment. You could then spin a teleology on this, and you can call it adaptive fitness. So you can measure the likelihood of the model evidence. If we now treat the phenotype as a model, and the exchange with the environment as the sensory data, then what you're trying to do is to maximize the probability of that exchange with the environment given the phenotype. And that just means that you are effectively, from a statistical point of view, able to fit the sensory data afforded by the environment with your model. So you now have a semantic coincidence between adaptive fitness and the ability of this phenotype as a model of its eco-niche to fit the sensory exchange with that eco-niche. But they're just expressions of surprise or marginal likelihood or model evidence. So if the nature exists, then in exactly the Markovian ergodic sense we're talking about before, there has to be it looks as if there's an upper bound or a minimization of surprise, or in fact you're not minimizing it necessarily, you're just not letting it explode, so that you're retaining yourself on this pullback attractor or this set of attractive states, which tells you immediately there has to be that. Remember when Don was talking before about these cyclical orbits and these so as soon as you realize the importance of that in terms of this Helmholtz-Hodge decomposition, we're talking about the solenoidal dynamics, you know that evolution has to have things like replication and reproduction and life cycles and biorhythms. These are just biologists' ways of understanding this cyclical aspect, which is fundamental to having an attracting set that is defined by the surprise. You find the surprise that measures the degree to which you're outside and violating that attracting set. So for me, it's all the same thing.
And how are these past states encoded? Like, is time constructed by agents or inference? And can subjective or physical time derive from conscious agents or generative models? How do you guys see that? Anyone can go.
I'll let Carl continue there.
Oh, right. So sorry, you're trying to cover your 8 themes. I can tell that. I thought I'm betting we've done all of them twice over by now.
These are them all in.
You gotta go. Yeah, not gonna miss out on one. Would time Well, I think time as a resource in terms of this counting and this terms of this ordering, yeah, to have evolution almost as it says on the tin, to evolve in some order. Now, is that order universal or clock time? I don't, I think you could argue about that. If there is universal or clock time, I'm not sure how you would measure it other than the information rates that we were implicitly talking about before. We're talking about sort of distances in some geometry. And these, for me, this would be an information geometry. So the distance now is an information length, which would be a path integral of infinitesimal KL divergences along the path from this probability distribution to this probability distribution. And then if you invoke the notion of universal time, you can now talk about movement in this on these statistical manifolds or attracting sets, and talk about the information rate as some metric of time. But does that necessitate time? I don't think so. As long as you've got some lawful ordering or sequence, the counter that Don was talking about, I think all the maths holds very nicely. Thank you. But would time, perceived time, be a useful icon, a useful minimum description length of this ordering and sequential stuff? Yeah, absolutely. Yeah. Mm-hmm. And then you get physicists who work in space-time backgrounds.
Right. I agree, and that word "useful" I think is the key. It's that the perceptions that we have were shaped by evolution to be useful, and useful and true are very, very different things. What's useful need not be true, and the argument from the payoff functions says that the probability that useful equals true is 0. Useful does not equal true except on a measure 0 subset of payoff functions, and so it's not impossible that we see the truth, but I would bet my life against it. Basically, it's infinitely improbable that anything that we perceive is anywhere near the truth. Now, I must say that most of our colleagues would beg to differ. They think that evolution has given us at least some access to certain aspects of the world truly, and also that the kind of argument that I gave, I've had philosophers publish articles in philosophical journals basically saying that I need to go learn elementary logic, because I've started off with evolutionary, Darwin's theory of evolution, which assumes that there are organisms in space and time real physical organisms in space and time competing for real physical resources like mates and food. And I give this evolutionary game theory argument, which then concludes that none of our perception, the probability that our perceptions are correct is 0, and therefore the probability that there are space-time and organisms and systems, organisms competing for resources in space and time, probability of that being true is 0. So the argument is, well, Hoffman, you assume space and time are fundamental, and organisms are fundamental, and then you go ahead and prove from Darwin's theory that they're not. So you shot yourself in the foot, and you just, you should go back and learn some baby logic before you start doing this kind of stuff. And my reply has been that this misses 2 key points about science and about logic. I'll do the science first. Science proposes theories, and each theory says, please grant me these assumptions. If you grant me these assumptions, then I'll explain all these other fun things. But the theory doesn't explain its assumptions, it assumes its assumptions. So no scientific theory is ever the theory of everything, because at a minimum, it doesn't explain its own assumptions. So there's always going to be, you can say, well, I can give you some new, deeper assumptions that will explain the previous assumptions and include the old theory. Hopefully, yes, but then your new theory will have its own assumptions. So this goes on ad infinitum. So there is no theory of everything in science, and not even close, because this goes on ad infinitum. So what that means is that every scientific theory, to the extent that it's a good theory, has some scope of explanation, but not infinite scope. It doesn't explain everything. It has a finite scope of explanation. Most of the ideas we come up with have no scope of explanation whatsoever. They're just wrong. But some theories have some scope of explanation. So a good theory, I'll call a scientific theory a good theory if it gives you mathematical tools to explore its scope and use it usefully. And I would call a scientific theory great if it gives you mathematical tools to actually understand the limits of its scope. Because we know there are limits to its scope. There's no question that there's a limit to its scope. The only question is the theory deep enough and well formulated enough to actually give you the tools to find its necessary limits, because it does have limits. And in the case, for example, of quantum field theory with Einstein's theory of gravity, that package of theories is a great theory because it assumes space and time are fundamental, and then proves that space and time as fundamental concepts fall apart at the Planck scale, 10 to the minus 33 centimeters and 10 to the minus 43 seconds. So without being self-refuting, Einstein's gravity with quantum field theory says we start with space-time and then we show you what had to be the case, that space-time cannot be fundamental. Here's where it falls apart. We can compute 10 to the minus 33 centimeters. Game over. And so that's just what great theories do. So so that's misunderstanding the nature of science when they say that science can't sort of refute its own assumptions. The best science does, because its assumptions cannot be the final word. So the best science actually does refute its own. But the logical side of it is, this is very much like Gödel's incompleteness theorem, right? Gödel starts with a set of, you said, grant me a set of axioms that are at least as rich enough to do arithmetic. And I will show you that it's incomplete. Now, for that argument, Gödel doesn't need to assume the truth of the axioms. He's assuming the consistency of the axioms. And same thing holds in science. When I put down a set of assumptions and then give mathematics to them and then show that those assumptions couldn't possibly be the final word, that there's limits to those assumptions, I'm not shooting myself in the foot logically, because I'm not assuming the assumptions are true. I'm assuming that they're consistent. And if they're consistent, then I can show that they can't ultimately be the final truth. And so this is a big point that I think holds a lot of people back. And this is not a minor point. It's really critical, I think, to understand that evolution entails the probability that anything that you perceive is true is zero. It's a very important fact about evolutionary game theory, is that you have zero probability of saying the truth. And that's why I'm saying, okay, space-time is just a headset. I mean, what evolution does give you is perceptions that guide adaptive behavior. That's what Darwin's theory gives us. It's saying our senses evolved to guide adaptive behavior. And I agree with that completely. And I stop right there. Most people then take the next step and say, oh, that means that you're seeing the truth. No. Your senses evolved to guide adaptive behavior, period. End of statement. Truth has nothing to do with it. And your headset, if you're playing a VR game, for example, and I see a red Ferrari in my headset and I'm trying to race against it or something. In that metaphor, the truth is some supercomputer that I can't see. And what I'm really doing is toggling millions of voltages at a very precise sequence at a very high speed. What it looks to me like I'm steering a steering wheel and trying to race that Ferrari. There's no Ferrari in the computer. But if I had to toggle all those voltages to play the game, I would lose the game. It's much, much easier to play the game successfully with my steering wheel and my red Ferrari than actually toggling the voltages in the computer. And so this is the way I interpret evolution. It shaped our sensory systems to be a user interface that guides adaptive behavior, period. Not the truth.
Carl, anything you want to say about that? As we round off, guys, just as final thoughts from both of you, where do you, before, Carl, if you'd like, you can comment before we go into that. Anything you want to add to that?
Well, yes, very briefly before we do the closing. Yeah, I agree. I agree with Don completely. And indeed, before I sort of looked at your face when you talked about falsification and the shame on your face when you realise that you use a falsification word.
Yeah,
I think you should be shamed by using the truth word. There is no truth pointing. Remember where we started? We started that the best and viable, maximum likelihood, most adaptive fitness, surprise minimizing, free energy minimizing explanation is a minimum description length. It means the probability that the real world generated the data in a way that you perceive it is zero, because there's always a simpler explanation for what's going on. This is actually a real practical issue when it comes to model comparison. It takes months to teach students there is no true model. There's only the best model. It's inference to the best explanation. There is no truth.
Yeah, that's precisely where I was headed now. I was just about to ask, where do you guys find that you most strongly agree with each other when it comes to everything we just discussed? Don, perhaps
It's constructed nature of reality, but with an acknowledgement that this is not an idealist position, that this actually involves the relationship of the thing that is conscious or is inferring or is observing to a wider context of which it will never know, but it can certainly make inferences. And I would say, I repeat, I think if you allow me to interpret Don's consciousness as Helmholtz's unconscious inference, I think we're exactly on the right page. Same page.
Don, same page. Where do you find you guys most strongly agree?
Well, I agree with what Carl just said, and the only thing that I would add to it is that in the case where I say that the observer, the context that the observer is observing is another observer, then we get something that looks like idealism, right? Because the objective thing itself is another conscious observer. So there is a way. I don't think you have to cash it out in idealist fashion, but it could be cashed out in idealist fashion in which it's observers all the way down, and the thing that I'm observing is just higher observers.
Yeah. And then where do you guys find you most strongly disagree? Perhaps, Carl, you can start. And what would change your mind?
Well, no, because what would change my mind?
Regarding the potential disagreement. And this is not, of course, a debate platform, but rather a constructive platform.
Sure.
I don't know if it's a disagreement, but I think what would need a lot more discussion and work was, and this is something I brought up with people like Chris Fields as well, who shares many of these commitments, is the nature of time. And he normally says to me, "Oh, the Wick's rotation or something," which is another way of getting the square root of -1 into the game. So I think if there was a point of conversation that needed to be resolved, I think it would be the notion that time can be dissolved by equipping things with a counter. And to me, there's something quite fundamental about time, which I'd like to understand. So it's not a disagreement, but it's something which is outstanding.
And for you, Don, where do you
agree with what
same place?
Yeah, I agree with Carl. Yeah, it's I don't see deep disagreements. I just see slightly different use of language, but going after the same concepts. So yeah, no, in the case of time, we have a counter for this Markov dynamics. It's not time. It's a counter. Time, as it's understood in physics, has no operational meaning past 10 to the minus 43 seconds. So that notion of time cannot be fundamental. And so, whereas right now I see no similar limit to this counter kind of notion, right? It seems to not have that kind of. But if I take the counter and I use this Markov dynamics, the trace logic to build space-time, then I will the projection of the counter into time will probably fall apart at 10 to the minus 43 seconds in that representation. So, but then I can imagine other representations of the counter that will have different cases where they fall apart. I should say, maybe as a sort of my final parting, and this is, again, not a disagreement with Karl or with anything we've said, it's more a step back from everything that I've done. Ultimately, one thing that the spiritual traditions say, like Rumi says, the language of God is silence, all else is poor translation. I agree with that. And I think that in some sense, whatever reality is, anything that we say will ultimately be at best useful, but not ultimately true. I think that the reason why some theories in science work and others don't is not because some are truer or not. I think that from a given perspective on whatever reality is, certain descriptions are good descriptions of that perspective of reality. But whatever reality is, and I don't know what it is, it transcends anything that we can talk about. So I'm not arguing against science. I'm a scientist. I love to do science, and I love to do mathematical descriptions, and I want them to be precise, and I want to throw away most of the bad ones. And yet there's another part of me that says reality, whatever it is like Rumi said, the language of God is silence. It transcends anything that we can ultimately say. And I am trying to come to terms with that. So I'm in process.
Well, guys, I mean, you both are incredible, and it's always a pleasure hosting the both of you. If just to close off, if you both had to write a joint manifesto, what 2 or 3 claims about mind, perception, or reality could you endorse without qualification?
I'll let Karl go.
I know it's getting late, Karl. For us it's quite late, but just
no, I know. And before you say goodbye, your viewers should know that our host actually has COVID, and our esteemed guest Don actually has long COVID, and it's me that's here. So congratulations on the two soldiering on. I need to say that. Sorry, what was the question? If I had to.
If you had to write a joint manifesto, what 2 or 3 claims about mind, perception, or reality could you endorse without qualification?
Well, that would certainly endorse the fact that reality is constructed. I think that's absolutely true. That we would try to avoid any baggage that has accumulated in physics, such as space-time, or I would actually also have probability amplitudes, or sort of microcanonical ensembles from statistical. These are all icons. They're all part of cultural niche construction that makes our job easier talking to each other as scientists, but they're not fundamental. So I think we'd certainly endorse that, and we'd certainly endorse the appeal to the best kind of icon, the best kind of language that we use to communicate, which would be maths. So, as noted before, that for Don, a good theory is that which can be applied numerically. And to my mind, that's what I was trying to intimate: the difference between a principle and a theory. A principle is useful; it does work for you, but it only does work in a formal setting. It won't write books for you, but it will run on a computer, or it will derive itself, in terms of mathematical analysis. Those would be my three things.
Done?
I'm completely on board. I agree. And I would add something else that I think that Karl has already said, that these kinds of ideas are really critical for thinking about the next generation of AI, going beyond large language models. I think that this, it won't be easy, but I think it's going to be an important way of moving toward a next generation of AI.
Well, guys, this has been absolutely fantastic. Thank you so much for your time. I know it's quite late. Some of us are sick, some of us are recovering, but I appreciate it very much. So thank you so much. Thanks for joining me again.
Thank you, Tevin.
Thank you.
Great.
Any final
Thanks a
thoughts?
lot.
Anything you guys feel like you missed, you haven't touched on, that you want to add on? Are you good?
I'm sure there are 101 things, but we also covered 101 things. So
That's right.
I feel quite proud and honored to have been part of this conversation. Thank you very
It
much.
was a great pleasure, Karl. Great pleasure, Karl and Tevin.
Thanks, guys. And I'll try and get some more in the future as well. So I appreciate it very much. Take care,
Okay. Take care.
guys.
Thank you. Bye-bye.